everybody. Good day. I hope you are safe now. So here I am. I'm making a video. By the way, I am Janice Garet, and together with Carl Vincent Chang and Janet Faith Patrocinio, we will discuss about sampling and reconstruction. So with me, you will watch a PowerPoint presentation, and I will try my best to deliver it with a simple and understandable way for you to understand certain concepts and ideas. So let's continue learning despite of this, crisis. So stay tuned and continue watching this video.
So let's begin. Sampling and reconstruction. So for the introduction, let's read this. Digital processing of analog signals proceeds in 3 stages. The first stage, the analog signal is digitized, meaning it is converted into a digital signal. It is sampled. So the one that is sampled here is the analog signal, right? And each sample quantized to a finite number of bits. This process is called ARD conversion. ARD meaning analog to digital conversion. So for this stage, you will need the sampler and quantizer. So this is the first stage, right? Ang iyahang na result is this digital input or digitized sample. So for the second stage, the digitized samples are processed by a digital signal processor. So this, kani siya, digital input, it is processed by digital signal processor. So mo na siyang maka-come up na siya og digital output. And for the third and final stage, the resulting output samples may be converted back into an analog form by an analog reconstructor. So, what do you mean by that? Ingon siya na kanidaw nga output, digital output, can be, kung ganahan ka nga i-convert into an analog output, you will need an analog reconstructor. And this third stage is called D or A conversion. Digital to analog conversion. So, this picture is a typical digital signal processing system. So, it is like converting an analog to digital and digital to analog. So, we're done with that. So, let's move on and review the analog signals. So, you already know what is analog signal, but here are the examples, the characteristics of analog signal. So, it is a type of signal, electronic signal, that is time varying, meaning it changes over time. Ang value niya, for example, voltage, it changes over time. That's why ang iyahang graph is like pura siyang sine waves gani nga balod ga balod. And then ang example ani niya is the temperature sensors, FM radio signals, photocells, and so on. It can be either periodic or non-periodic. Analog signal works on continuous data. The accuracy of the analog signal is not high when compared to the digital signal. Of course, we are aware of that. Nga ang accuracy sa analog signal ay siya kaayo sa digital signal. Mas accurate ang digital, diba? It helps you to measure natural or physical values. Analog signal output form is like curve, line, or graph. So, to visualize an analog signal, so, naata dire graph. Okay, so, please see that graph, no? Kani siya nga side, this y-axis, mo na ito ang value. And ang example diri niya is ang voltage. So, this is time. And so, if the voltage is, changing over time, varying in time, mo nang inana ng iyahang graph. A time versus voltage graph of an analog signal should be smooth and continuous. As you can see, smooth siya, wala siya like putol-putol or what. And then smooth siya, continue siya, wala siya nagaputol-putol. So, that's it. And let's go to the first main topic of our of the chapter 1, which is the sampling theorem. Under this is the sampling theorem, anti-aliasing pre-filters, and hardware limits. So before we tackle what is sampling theorem, let's define first what is sampling. So sampling is a conversion of continuous time signal. An example of this is analog signal into a discrete time signal or digital signal. Taking samples of the continuous time signal at discrete time instance. The sampling interval is t. So kanisha, this is the sampling formula or equation. So the discrete time signal kaning xn is obtained by taking samples of the analog signal x t every t second. So mo ni siya. Please refer to this equation. The time interval t is called sampling period or sampling interval. The sampling rate or the sampling frequency is found as fs equals to 1 over the sampling period. And of course, this is in units of hertz. The relationship between the variable t of analog signal and the variable n of discrete time signal is t is equals to n times t. So, t ani is, from this, 1 over fs, diba? So, n times 1 over fs. So, that is n over fs. So, mana siya. And then, mo ni siya katong sa formula, diba? From analog signal into a digital signal or discrete time signal. So, mo ni siya nga form. Then, gisampled siya. Mo na siya mo na result. From this to this. So, let's go to sampling theorem. Sampling theorem gives the criteria for a minimum number of samples that should be taken. So, na siya is something like for siya gani given basis nga that should be taken, diba? Sampling criteria. Sampling frequency must be twice of the highest frequency. So, this is it. Fs equals to 2W. Fs is the sampling frequency, W is the higher frequency content, and 2W also known as Nyquist rate. So we're done with the sampling theorem, and let's go to anti-aliasing pre-filters. So before discussing this, let us define what is aliasing. Aliasing is an interesting and usually unwanted phenomenon that happens when a signal is sampled at less than the double of the highest frequency contained in the signal. So sa kasampling theorem, Fs equals to 2W. Muna siya may criteria. But sa aliasing, nahimo siyang Fs is less than 2W. So that's why na aliasing. Kung mayroon kang aliasing, it is the unindistinguishable frequency. As you can see sa picture, mara siya og like distorted, like dili kay siya tantong smooth, dili kay siya perfectly graph gani. So that's it. Muna siya aliases or jaggies ba to. And then in order to sample a signal at the desired rate and satisfy the conditions of the sampling theorem, the signal must be pre-filtered by a low-pass analog filter. Munang mosulod si anti-aliasing pre-filters. Kay para makorek ni siya. Kay less than man siya sa double of the highest frequency based sa sampling criteria. Munang ganid ka og anti-aliasing pre-filter. So next, the effect of aliasing. Distortion. The data is lost and cannot be recovered. To avoid aliasing, the sampling rate must be Fs greater than 2W. Strictly bandwidth the signal to W. Kani siya mo ni nga side Strictly band limit the signal to W. Muna siya. So next, let's go to hardware limits. The sampling theorem provides a lower bound on the allowed values of Fs. The hardware used in the application imposes an upper bound. So lahi daw sila. Like, ang sampling theorem is up sa lower bound. Ang hardware is upper bound. In any case, there is a total processing or computation time, say t proc seconds or t processing seconds, required for each sample. The time interval t between input samples must be greater than t processing. Mo ni siya dire, oh. Must be greater than daw. Otherwise, the processor would not be able to keep up with the incoming samples. Or expressed in terms of the computation or processing rate, f processing equals to 1 over t processing. Like, ning frequency ni siya. Yan kani siya may period t period of processing. We obtain the upper bound fs less than greater than the sampling frequency is less than equal to the frequency of processing, which combined with equation 1.3.2 restricts the choice of fs to the range. So mo ni siya nga range to f max less than equal to fs less than equal to f processing. So mo na siya. So we're done with the sampling theorem. So let's go to the second main topic, sampling of sinusoids. So under this is the analog, reconstruction, and aliasing, rotational motion, and frequency units. So next, the two conditions of the sampling theorem, namely the x function of t be band limited and the requirements fs greater than equal to f max, can be derived intuitively by considering the sampling of sinusoidal signals only. Figure 1.4.1 shows a sinusoid of frequency f. X function of t is equals to cos 2 pi ft that has been sampled at the three rates fs equals to 8f, 4f, and 2f. These rates correspond to taking 8, 4, 2 samples in each cycle of the sinusoid. So, diba, naman na siya sa kuan. Naman to siya giingan nga, pero siya cycle. So, fs equals to 8. 1, 2, 3, 4, 5, 6, 7, 8. So, 8f. 1, 2, 3, 4. Mura dyan niya akong na-observe po dyan. 1, 2. Muna siya. 2f. So, sinusoid sampled at rates. So, kani siya may rate. Rate niya. Mga rates ni siya. 8f, 4f, and 2f. So, next. Simple extraction of these figures leads to the conclusion that the minimum acceptable number of samples per cycle is 2. 2 daw ang minimum. Remember that. The minimum acceptable number of samples per cycle is 2. The representation of a sinusoid by 2 samples per cycle is hardly adequate, but at least it does not incorporate the basic up-down nature of the sinusoid. The number of samples per cycle is given by the quantity fs over f. So samples per second all over cycles per second equals to samples per cycle. Thus, to sample a single sinusoid properly, we must require fs over f greater than equal to 2 samples per cycle. So mo giingon niya nga at least ang minimum niya is 2 samples, diba? But dili na siya kanang like mumubo sa 2 samples per cycle. Or kanang kuan siya like so man mo ni siya fs greater than equal to 2f. Mo na ni siya simplified equation. Next, consider the case of an arbitrary signal x function of t according to the inverse Fourier transform of x to the function of t can be expressed as a linear combination of sinusoids. Kaning inverse Fourier transform like kuan siya, maraming siya tools gali somewhat sa pag-convert Japan. Proper sampling of x to the function of t will be achieved only if every sinusoidal component of x function of t is properly sampled. Be achieved only if every sinusoidal component. So, ang proper sampling, ma-achieve siya only if every sinusoidal component xt is properly sampled. So, dapat properly sampled sila tanan. This requires that the signal x function of t be band limited. Otherwise, it would contain sinusoidal components of arbitrary high frequency f. And to sample those accurately, we would need by equation 1.4.1 arbitrary high rates if the signal is limited to ano man eh napadere to some maximum frequency f max. Then by choosing fs greater than equal to f max, we are accurately sampling the fastest varying component of x of t, and thus a fortiori all the slower ones. As an example, consider the special case x function of t a1 cos 2 pi f1t, and so on, where f1 are listed in increasing order than the conditions to f1. Okay. Imply that every component of x function of t, and hence x function of t itself, is properly sampled. So, to be properly sampled daw, the signal should be band limited. And dapat masatisfy ni siya nga condition kani nga side. Okay. Para maiwasan ang like kanang results gali nga ang sum of the sinusoidal components of arbitrary kanang ma-high frequency siya, dili siya like accurate or like good. So dapat kuan siya kanang masatisfy ni siya nga condition. The sinusoidal should be sampled properly to have a proper sampling. Okay. So that's it. And Janet will continue the remaining one of the remaining topics. So thank you for listening, and I hope you learned something from me. I hope. Thank you.